To understand the basic physics of climate change, one has to think about the Earth's radiation budget. Now, we measure the Earth's radiation budget in units of energy per unit time per unit area. The reason for this is that we think about how much incoming radiation energy there is per unit time, so that would be a unit like a watt, per square meter, which then tells us how much energy is received per square meter of the Earth's surface. Now, the Earth's surface temperature in general is controlled by the solar radiation the Earth receives from the sun. There is a small amount of geothermal energy that the Earth receives from the internal heat of the Earth. That flux is something like 1/10 of a watt per meter squared on average. That's really tiny compared to the solar radiation, which is several hundred watts per meter squared. At a very superficial level, we can think of the incoming solar radiation being mostly in the visible spectrum, which is short wavelength. That is the visible light we see, also a little bit of ultraviolet light. And that penetrates the Earth's atmosphere, and some of it is reflected by white clouds, some of it is reflected by white things on the surface, like deserts or like ice sheets, and that light then would be reflected back to space. But whenever the visible light actually hits something darker on the Earth's surface, that material absorbs the energy and heats up a little bit in response to the energy flux that it receives from that solar radiation. As you know, when you go outside on a sunny day, you feel the warmth in response to your body encountering the solar radiation from the shortwave radiation, and you absorb that energy and turn it into heat. Well, heat itself is a form of radiation, but at a longer wavelength. And so we emit that heat back to the atmosphere. So when the surface of the Earth absorbs the visible light that it receives from the sun, the temperature increases and radiation is radiated back out towards space, so that essentially there's an exchange of shortwave for long-wave radiation. Over a relatively short timescale, there's an energy balance, so that the amount of incoming energy from the sun is balanced by the amount of outgoing energy, which is a combination of both the sunlight that's reflected directly back to space and the long-wave radiation that comes from the interaction with the Earth's atmosphere and the surface, and it's heating up and radiating long-wave radiation. And so you can actually match up the incoming shortwave radiation with the outgoing shortwave plus long-wave radiation. In this context, one can think about the role of greenhouse gases as increasing the surface boundary layer of the Earth. What greenhouse gases do is they absorb infrared radiation, long-wave radiation, as it's coming off the surface, and ultimately then re-radiating that back down and back out to space. The reason they're called greenhouse gases is that they work much like a greenhouse. A greenhouse is a glass enclosure where it lets in visible light from the sun and heats up during the day, but because the glass is relatively opaque to infrared radiation, to long-wave radiation, the heat stays inside even though the visible light can penetrate. And as a result, the temperature inside a greenhouse on a cold, sunny day is much, much hotter than what it would be outside. Essentially, that's what's happening with the entire atmosphere of the Earth, where the greenhouse gases essentially give you a layer, much like covering yourself with a thick comforter on a cold night. They essentially absorb infrared radiation, re-radiating it back to space and back down to the surface, but essentially increase the altitude at which the Earth is in this energy balanced state where the incoming radiation is the same as the outgoing radiation. One way to think about the Earth's energy budget is to compare the Earth with our neighboring planet Venus. So Venus is about the same size as the Earth, and it's closer to the sun, so that means it gets roughly twice as much solar radiation per unit area as the Earth. So you would expect Venus to be a lot hotter, and sure enough it is. It's about 460 degrees Celsius at the surface of Venus. It's pretty steamy. But if you look at the energy budget of the two planets, one actually sees that Venus being closer to the sun is not the primary reason why Venus is so hot. The Earth gets about 340 watts per meter squared of incoming solar radiation on average around the Earth's surface, and about 100 watts per meter squared of that is reflected back to space. Most of it is from bright clouds in the Earth's atmosphere. A little bit of it is from the surface of the Earth and from especially the polar ice caps that are very white. So a little more than 2/3 of the incoming solar radiation is actually absorbed by the Earth's surface and is turned into heat and ultimately to outgoing infrared radiation. In contrast, the surface of Venus is much, much brighter than the Earth. Venus receives about 650 watts per meter squared of incoming solar radiation, but almost all of that, roughly 500 watts per meter squared, is reflected back to space because the surface of Venus is so bright. In truth, the situation with Venus is a little more complicated because it's not the surface of Venus that's so bright and reflecting the sunlight. It's actually the atmosphere itself. There's a lot of sulfate aerosols in the Venusian atmosphere. And so figuring out exactly what the albedo of Venus would have been if it had the same atmosphere of the Earth is a hypothetical question that's kind of difficult to solve. But the real point is that it's not being closer to the sun that makes Venus so hot. It's actually its ultra-greenhouse atmosphere. What that means is that if the Earth and Venus had the same atmosphere, Venus would actually be colder than the Earth, even though it's closer than the sun, because the amount of solar radiation that's actually absorbed at the planetary surface is actually much smaller than the Earth. And therefore, if it had no greenhouse gases in the atmosphere, or if it had the same amount as the Earth, it would be substantially colder. Venus's atmosphere is 100 times denser than the Earth and composed almost entirely of carbon dioxide, as well as some other trace gases that make it a very powerful greenhouse atmosphere. And that's why the surface of Venus is 460 degrees Celsius. In contrast, the atmosphere of the Earth has a very strong greenhouse effect. The total greenhouse effect is about 30 degrees Celsius. So that means that if we didn't have an atmosphere, the Earth's surface temperature would be about 30 degrees colder than it is today, but it's still mild compared to the ultra greenhouse on Venus. Let's take a look at the energy balance of the Earth in a little bit more detail. The first thing we have to talk about is the wavelength of different types of radiation, of different types of light. If we look at the electromagnetic spectrum, we can describe different types of radiation, different types of light, as having different wavelengths. So visible light has a wavelength between 0.7 and 0.4 micrometers or microns. Ultraviolet light has an even smaller wavelength, below 1/10 of a micron. And infrared radiation, what we think of as heat, has a much longer wavelength, from about a micron up to about 1,000 microns. There are also microwaves, which have even longer wavelengths, and also X-rays, which are much shorter wavelengths than ultraviolet radiation. And the other important thing to remember is that the wavelength is inversely correlated with energy. That is, high energy radiation has shorter wavelengths, and lower energy radiation has higher wavelengths. We'll come back to this in a minute. When we think about planetary energy balance, we often talk about a black body radiation. What we're thinking about here is a body, like a planet, that is black so that it actually absorbs radiation at all wavelengths. And black body radiation describes how the infrared radiation emits as it heats up, as a function of temperature. There's some basic laws of radiation that we need to cover. First, all objects emit light, emit radiant energy. And hotter objects emit more energy than colder objects. So the amount of energy radiated is proportional to the temperature of the object. It's actually a little more complicated than just directly proportional. It actually goes as temperature to the fourth power. This is what's called the Stefan-Boltzmann law, and we often call it black body radiation. It describes the flux of energy as a function of the surface temperature of the object. We have a simple equation here where F is the flux of energy measured in watts per meter squared, T is temperature raised to the fourth power, and sigma is a constant that is universal across all black bodies. The last thing we need to know is that objects that are hotter emit light at shorter wavelengths. This is called Wien's law, where the wavelength of light equals 3,000 divided by the temperature in Kelvin. So let's take these two radiation laws. The Stefan-Boltzmann law that describes the radiation flux from a black body as a function of its temperature, and the Wien's law that describes the wavelength of light from an object. Let's consider two objects in our solar system: the Sun, which is the source of our energy, and the Earth. The Sun is roughly 6,000 Kelvin at its surface, and the Earth is about 300 Kelvin at its surface, a little bit less than that. If we apply Wien's law, the Sun emits light at a wavelength of about half a micron. That's right in the middle of the visible spectrum, whereas the Earth emits light at about 10 microns, which is in the infrared spectrum. So that explains basically why you get this energy balance between shortwave and long wave at the Earth's surface. If we take those temperatures and plug them into the Stefan-Boltzmann law, where we raise the temperature to the fourth power, we get that the flux of energy from the Sun is about 7 times 10 to the 7th watts per meter squared, whereas the flux of energy from the Earth is about 460 watts per meter squared, much, much less. That's not that surprising. Let's dig a little deeper into the Earth's energy balance and its interaction with solar radiation. We have to remember first some basic geometry, that the area of the circle is pi r squared. We're going to approximate the Earth as a circle, even though it's not perfectly circular. And of course, the area of a sphere is 4 pi r squared. We can describe a simple energy balance where the amount of energy delivered to the Earth from the Sun is equal to the energy lost from the Earth as infrared radiation. If it wasn't in balance over relatively short timescales, the Earth would heat up or cool off, depending on whether it had an excess of energy or a deficit of energy. So we can write this very simple energy balance equation that just says energy in equals energy out. So how much solar radiation reaches the Earth? Well, remember we said that the Sun emits 7 times 10 to the 7th watts per meter squared, but of course, as the Sun's energy is emitted out to space, only a very small fraction actually reaches the Earth because it's spread out over a greater and greater area. That means that every planet has its own solar constant because it's a different distance away from the Sun. Planets that are further away from the Sun, that energy from the Sun is spread out over a much greater area, a greater sphere, and therefore they have a very much smaller fraction of that total solar energy. So if you think about this from the perspective of the Sun, solar radiation is traveling towards the Earth and sees a circle that would be the side of the planet turned towards it at any one time. That would be just a circle defined by the Earth's radius. So we can write this simple equation where the incoming energy is just equal to the solar constant, S naught, times pi r squared. But it turns out this isn't quite correct, and the reason we already talked about is that not all of the solar energy reaches the Earth's surface. Some of it is reflected away, both by clouds, by aerosols in the Earth's atmosphere that we'll talk about in a minute, and also by bright areas of the Earth's surface. So we have to describe something called albedo, which is the percent of shortwave radiation that is reflected back to space and is never absorbed and turned into heat. So we adjust the total incoming solar radiation, S naught times pi r squared, by a factor 1 minus A, where A is the albedo of the Earth, and that just describes the fraction of incoming solar radiation that's actually absorbed by the Earth's surface and turned into heat as opposed to direct reflection back to space. The Earth's albedo today is about 30% or 0.3. So about 70% of the incoming solar radiation is actually absorbed by the Earth's surface. So to complete the energy balance, we have to describe how much energy the Earth emits. The energy out is just equal to the total flux of energy from the Earth as a black body times the area of the Earth. Using the Stefan-Boltzmann equation, we can calculate that the flux out is simply sigma times t to the fourth times 4 pi r squared, the surface area of the Earth, because the Earth is emitting energy from all of its surface at any one time. So if the energy in equals the energy out, we can now expand this simple equation, canceling pi r squared from both sides of the equation. We end up with a simple relationship where S naught times 1 minus the albedo equals sigma t to the fourth times 4. Or rearranging, we get t to the fourth power equals the solar constant times 1 minus the albedo divided by 4 sigma. We can plug in our known values for these different constants here. So the solar constant is 1,370 watts per meter squared. The albedo is 0.3. sigma, the Stefan-Boltzmann constant, is 5.67 times 10 to the minus 8. So when we plug all those constants in, we get a surface temperature of 255 Kelvin, or about at minus 18 degrees Celsius. Wait a second. That's a little bit too cold for the surface of the Earth. What did we do wrong? Is the Earth's surface really minus 18 degrees Celsius? No, of course not. It's really about 288 Kelvin, or about 15 degrees Celsius. We have a problem. The difference between what we observe, about 15 degrees Celsius, and the calculated temperature, minus 18 degrees Celsius, is about 33 degrees. Why are we off by 33 degrees? Why is the Earth's surface 33 degrees warmer than we would expect from this simple energy balance calculation? The answer, of course, is the atmosphere, the greenhouse effect. Our calculation assumed that there was no atmosphere at all. It was just a black body radiation calculation, assuming that the Earth emits directly to space and that the surface of the Earth is in radiative equilibrium directly. Because the Earth has an atmosphere, it's about 33 degrees warmer than it would be otherwise. That's why the greenhouse effect is so important. So let's see how our discussion of the Earth's radiation balance actually applies to the recent history of surface temperatures on the Earth. We know from instrumental records and also a variety of proxy records that we'll talk about later in the course that the Earth's surface temperature has fluctuated a bit over the last 1,000 years, but over the last 100 years we've seen a very strong warming trend. From about 1900 to 1940, where temperatures warmed up a little bit, then they stabilized, maybe even cooled just a little bit through the mid-1970s, and then warmed very steeply from about 1976 through the year 2000. From the Stefan-Boltzmann equation, where the flux of outgoing radiation is equal to sigma times T to the fourth, we can quickly see that that 0.7 degree global warming has resulted in, if we take 288.7 to the fourth power over 288 Kelvin to the fourth power, we end up with a difference of about 1% in outgoing long-wave radiation. That's roughly 3 watts per meter squared. So over the course of the last 150 years or so, the Earth's outgoing radiation should have increased by about 3 watts per meter squared. How can we explain that? Well, the answer has to do with a rise in greenhouse gases in the atmosphere. We tend to focus on carbon dioxide, and carbon dioxide is certainly going to be the main focus of this course. We'll talk a lot more about the rise of carbon dioxide that we see here in the famous Keeling curve from Mauna Loa in Hawaii, and why it actually goes up the amount it does. But it's important to remember that carbon dioxide is not the only greenhouse gas. If we think about this in terms of a radiative balance, we see that CO2 is the largest greenhouse gas, but it's certainly not the only important one. This graph shows the cumulative effects of different changes in the Earth's surface on the radiation budget. The increase in carbon dioxide has had an effect of about 2 watts per meter squared, but other greenhouse gases are important. The next most important greenhouse gas is methane, or CH4, and also nitrous oxide, N2O, and also halocarbons, which are a variety of very rare compounds that actually have a very large greenhouse effect. There's another important greenhouse gas, which is ozone, or O3. We normally think of ozone in the stratosphere, where it actually protects the Earth's surface from ultraviolet radiation that would be very harmful to most living things. In the stratosphere, ozone actually has a cooling effect. In the troposphere, ozone is a pretty powerful greenhouse gas and generally comes from pollution, from a variety of chemical reactions that occur when different types of pollution mix. There are also the effects of changes in land use on the Earth's radiation budget. When we cut down forests, for example, and plant agricultural fields, we tend to increase the Earth's albedo and cool the planet a little bit. And when we release a lot of soot from burning of different types of fuels, and that soot settles on snow and ice, it darkens the surface of the snow and ice and increases the surface temperature. There's also a very powerful cooling effect of human activities on the atmosphere. This is the release of sulfur dioxide into the atmosphere, which rapidly gets oxidized to sulfate. Now, sulfate particles in the atmosphere, we call them sulfate aerosols, are very bright, and they directly reflect a lot of sunlight. They also interact with water vapor in clouds and tend to make the clouds very bright as well. And so there's a direct and also an indirect effect of sulfate aerosols. The direct effect being directly reflecting light, but indirectly they also influence how clouds reflect light overall. One of the big mysteries about the Earth's radiation budget over time is exactly how much sulfate aerosol has been released. Most sulfur dioxide comes from coal burning or from the combustion of diesel fuel or heavy oil, like from ships. And the sulfur dioxide rapidly turns into sulfate and then rains out very quickly. So the average lifetime of sulfate aerosols in the atmosphere may only be a week or two. Every now and then, a large volcano goes off and injects sulfate aerosols into the stratosphere, and that can last a little bit longer, up to a year or more. We'll talk about this later in the course. But exactly how much sulfate aerosols in the troposphere have cooled the climate over time is a big question mark. You can see on this graph how large the error bars are for both the direct and indirect effects. So the overall radiative balance of the Earth is still a big question, mostly because we don't know exactly how much effect sulfate aerosols have had on the surface temperature over time. We can think about these different effects when we look at the pattern of surface temperature rise over the past 100 years. The dominant theory for why surface temperatures stabilized or even fell a little bit between the 1940s and the 1970s is that this was a time when we started to burn a lot more coal and a lot more sulfur emissions from liquid fuels. And as a result, the sulfate aerosols increased dramatically and overwhelmed the greenhouse effect, essentially canceling it out and leading to no rise in surface temperatures. But because sulfate aerosols are short-lived, whereas the carbon dioxide accumulates, as we'll discuss a little bit later on, eventually the carbon dioxide started to win out and temperatures shot up by the mid-1970s. Indeed, Wally Broecker, a famous scientist at Columbia University, wrote a paper in 1975 predicting exactly that the short timescale effect of sulfate aerosols would soon be overwhelmed by the longer timescale of greenhouse gases, and that we were due for a very large rise in surface temperatures. I don't think Wally had any idea that he was going to be so precise in his prediction that when that paper was published was pretty much when the temperatures turned around. But this interpretation is still being debated today, especially in the context of the current plateau in surface temperatures since about the year 2000. If you step back and look at the whole record, the recent plateau from the year 2000 looks a lot like what happened from the 1940s to the 1970s, and it seems like it should have the same explanation. And indeed, there's been a huge increase over the last 15 years in sulfur emissions, predominantly from China and Southeast Asia. China now burns more coal than the rest of the world combined. And that acceleration in coal use by China, and also diesel use and oil use, has really occurred over a relatively short period over the last 2 decades. But some people question whether sulfate aerosols is actually the explanation, both for the mid-century hiatus and also for the more recent plateau. Another idea is that the excess radiation, because of the rise in greenhouse gases, is actually being balanced by heat uptake from the oceans. In this explanation, the Earth is actually out of radiative equilibrium, that the extra energy received does not result in an instantaneous rise in surface temperature, but a slow warming of the deeper ocean. The deeper ocean, of course, is very large and has a huge heat capacity. It stores enormous amounts of heat. So a small imbalance in the Earth's radiation budget of a watt per meter squared or so can easily be accommodated by a slow warming of the deeper ocean.